Okay, here you go.
Hey Typhoon, how's it going?
Yeah.
Nice to see you again.
So here we are introducing our speaker of the day, Professor Martin Bizzarro. He's not new as a colloquial speaker. He had visited us before, but before pandemic. And so he actually visited us in the period 2017, 2018, and other times to visit our nanosynth. Professor Martin Bizzarro actually got his degree from University of Quebec in Montreal. And then he arrived in Copenhagen in 2003, and he started where he is a director of Center of Star and Planet Formation called StarPlan that's there. And now as part of Globe Institute, and he has established a multidisciplinary group with people working from theoretical investigation, observation, and lab investigation. So that's welcome.
Thank you. Thank you, Sienna. It's great to be in Taipei again. And today, the topic of my talk is to explore this idea that interstellar ices in the early solar system were a reservoir of supernova nuclides. And if that's correct, it has important implication for the origin of these isotope anomalies that we see in the solar system, because ices would be a carrier that is volatile as opposed to be refractory like pre-solar grains. And so this is a collaboration with many people, which I haven't put them here, but it's not just me. So there are a number of my students and colleagues at the center which are working on this topic. Okay, so I'm not going to teach you anything with this, but this is basically going to the pathway of forming planets in our solar system. There's a molecular cloud material which collapses due to its own gravity into a disk, a protoplanetary disk, a young stellar object surrounded by a disk of dust and gas. And from this disk, the planets eventually emerge. And if we look at the ingredients which are important in this constellation, the molecular cloud material is basic. This is where the raw ingredients are present, and we have a micron-sized material. We have stardust, so grains which were made in exploding supernova or AGB stars, containing some of these metals. We have organics and interstellar ices. This material collapses and is thermally processed in a protoplanetary disk to form millimeter-sized solids, and eventually these solids, they will accumulate to form the final products, planetary bodies. And there's a lot of debate currently as how do we form planets? Do planets form in this stage here, in the very early stage during the first 3 to 5 million years, or do planets form 100 million years after the formation of the sun? So we'll touch a little bit on that today. A concept that is important to remember when in cosmochemistry is that we estimate the bulk solar system composition using a type of chondrite which is known as CI chondrite. And that's because if we compare the composition of the solar photosphere with these CI chondrites, we can see that their chemical composition matches that of the sun for non-volatile elements. So we think this is the bulk. When we analyze CI chondrites, it's the bulk composition of the solar system. And CI chondrites, they're a rare type of chondrites, carbonaceous chondrites, which are essentially made of matrix minerals. So phyllosilicate minerals, minerals which are formed by the interaction of water ice and pre-existing amorphous grains. And so they are not found very often on Earth. There's only 4 or 5 CI chondrites that have been reported. But interestingly enough, and this is just a little sidestep, for those of you who are a bit familiar with sample return missions, as you may know, we've landed and brought back material from 2 carbonaceous asteroids, the Ryugu asteroid, this is the Japanese Space Agency, and Bennu asteroid, this is NASA. This is approximately 500 meters in diameter, and this is close to a kilometer. But the interesting thing is that the first time that we land on a C-type asteroid, the composition of this material is very, very similar to CI chondrite. So if they cannot, statistically speaking, it would mean that this material must be widespread in the asteroid belt if we land on for the first time and it's a CI chondrite. So the fact that we don't have CI chondrite in our collection is probably because they are very fragile and they don't survive atmospheric entry. Okay, so let's focus on chondrite meteorites in general and talk a little bit about them. So chondrites are more or less cosmic sediment. They are made of essentially a high temperature component and a low temperature component. So the high temperature component, this include refractory inclusions and chondrules. So chondrules are the spherules, here silicate spherules, which were molten and free-floating object in space before they were accreted in the chondrite parent bodies. We don't exactly know the formation mechanism, it's highly debated, but they are the most abundant constituent of chondrites. Refractory inclusions, these are the earliest solids. These are the white spots here, one here and here and here. And these are condensate. And we date the age of the sun or the age of the solar system by dating these condensate. And this has been done actually in my lab in 2012. And the age of the sun, we take the age as being 4.567 billion years old with an error of approximately 100,000 years. Now, there's another very important component, and this is the one that we're going to be focusing on today, is the low temperature component. And this is what we call the fine grained matrix. This is basically what binds together these high temperature components. And the matrix preserve evidence for aqueous alteration. So the majority of the chondrite meteorite that we have in our collection show that there was water ice circulating on these parent bodies. And the interaction of the water with pre-existing minerals made new minerals, which we call clays. We'll be focusing a little bit more on these minerals later. So just to provide a bit of chronological background on the formation of these different objects before we get into the more specific part of the talk. This is a summary of early solar system chronology. So you have the time after formation of a protosun here. Note that the scale is logarithmic. The lifetime of the disk is approximately 4 to 5 million years. If we look at the formation timescales of the first solids, condensation and melting of these refractory inclusions that I just told you that define the age of the solar system is in the first 100,000 of years. The chondrules in the first million years, that's the primary production, and then we have recycling and remelting of these pre-existing chondrules. If we go to the timescales of formation of the bodies themselves, so the meteorites which come from differentiated body like Vesta, for example, we believe that they must have formed very early in the first few 100,000 of years, and that's because the only source of energy that is capable of melting these bodies is aluminum-26. And aluminum-26 was discovered by Typhoon, which is sitting just right here, so that's quite relevant. We believe that Mars would also form on similar time scale as the achondrites. And the chondrites, they are not molten because they form after the decay of aluminum-26. So that's the reason why they are chondrites. They form late during the evolution of the protoplanetary disk. So because chondrites are not molten, they contain all the raw ingredients which were present in the molecular cloud, including ices, organics, and these presolar grains. So presolar grains are grains that were formed in dying stars. They're older than the solar system, and they survive the formation of our solar system. So there's a number of generation of these grains or type of grains. So silicon carbide, very abundant type of presolar grain, graphite grains, diamonds, and now people have discovered silicate grains, which are more challenging to work with because they are extremely small, approximately 500 to 200 nanometers. So that makes them very difficult, and of course the instrument of choice to study these type of material is the nanosims. Okay, how do we recognize these presolar grains? Well, these presolar grains have isotopic composition, which is highly anomalous relative to the solar system. And for example, here I'm showing the nitrogen versus carbon isotope. You see the mainstream silicon carbide grain here, which are derived from AGB star. They're the most abundant type of silicon carbide. And there's other types of grains, which, for example, the X grains, which are supposed to be supernova grains, and the Z grains. But the point that I want to make here is that the traditional interpretation that there's isotopic variability in the solar system for some of these elements, some of these nuclides, is because we have incorporation of variable proportion of these grains. And this is the hypothesis that I want to challenge today, because I'm going to try to convince you that actually interstellar ices are more important in generating variability compared to these grains here. So a very important discovery in cosmochemistry, which dates back to almost 20 years now, is that there is a systematic difference in the isotopic composition for stable isotopes between different regions of the solar system. So there's sort of a gradient that exists. And this is one of the original papers published by Anne Trinquier in 2007. And this is one of the nucleosynthetic tracer that we use is chrome-54. And chrome-54 is a stable isotope, but you can see that in this epsilon nomenclature here, which is the 10,000 per 10,000 deviation of material relative to the Earth, which is 0, you can see that the carbonaceous asteroids record excess in 54 chromium, whereas the inner solar system, which is characterized by Mars, by Vesta, by other types of meteorites, record deficits here. So it has long been postulated that the reason why we have this variability is because we have, for example, these highly anomalous pre-solar carriers of chrome-54, and if you have more of this carrier here and less there, for some reason in the early protoplanetary disk, you're going to create these differences here. So to make a long story short, if we accept that the carbonaceous material as well as cometary material form in the outer solar system, so let's just say beyond 2.5 AU, and the ordinary chondrite, the Earth, Mars form in the inner solar system, well, there is this sort of a stratigraphy, so to speak, where or radial gradient where we have material in the outer solar system which is enriched in supernovae dust and material in the inner solar system which is depleted. And so people have been using these nucleosynthetic tracers a little bit like DNA to actually try to fingerprint what is the Earth made of. Is the Earth made of a mixture of these two reservoirs, or is the Earth essentially made of inner solar system material? And that's highly debated in the community now. So one view, I'm going to introduce the two views now. One view using these nucleosynthetic anomaly, and I'm showing you here zirconium-96. We'll be talking about that today. But I'm showing you a plot from this relatively recent paper looking at 50 titanium, so another tracer, a little bit like chrome-54, and 96 zirconium. And this is the Earth here, and this is Mars and inner solar system material. And you can see that in this diagram here, Earth lies as an M-member composition. And so these authors argue that, well, Earth must have formed from material which doesn't exist in our collection because it's an M-member composition here. So Earth must have formed from an unsampled inner solar system reservoir. And if the Earth is formed from locally derived material, it suggests that it formed by slow collisional growth over timescales of 100 million years. So that's the traditional terrestrial planet formation mechanism that is favored in this interpretation here. So again, just to make the point here is that in this model we form relatively early planetary embryos, and then it takes about 50 to 100 million years for these embryos to slowly collide together to form the terrestrial planets. So the opposite view is the one that I've been proposing in Copenhagen in my group, and that view is actually that the planets actually form much more faster. They form during the lifetime of the disk by the mechanism of pebble accretion. And one of the evidence for that, this is a new paper. We have a series of papers basically looking at different tracers, but this is a new cosmochemical tracer. It's silicon. And we've developed that a couple of years ago. The paper was published in 2023. but it's an important tracer because that's the main building block of planets. Silicon is a major element, and that's what the planets are made of. And what you can see here is that this is the inner solar system, so chondrites, Vesta, Mars, and these are the carbonaceous chondrites. So the Earth is basically a mixture of these two components here. So this model, or these new data for silicon isotope, favor a model where we don't form the Earth 100 million years after T0, but we form the Earth during the disk lifetime. And one of the reasons that it's important to distinguish between these models is because if we form Earth in the inner solar system from locally derived material, the Earth is formed dry, and we need a stochastic process to bring the volatiles to the Earth. If we form the Earth during the disk lifetime as outer solar system volatile-rich material is drifting in the disk, the volatiles that are critical to life are actually the building blocks, part of the building blocks of Earth. So that would imply that if planets formed by pebble accretion, the presence of volatile is a predictable outcome of this planet formation mechanism. Okay, and so I'm just going to speak a little bit towards why is there some variability in the inner solar system, and what models are trying to explain the fact that you have supernova enriched material in the outer disk and supernova depleted material in the inner disk. And one of the models that has been put forward is that there is thermal processing in the inner disk. The temperatures are hotter, and we are basically destroying some carriers of isotope anomalies and depleting the midplane disk, the solids, and enriching a gas phase. And I'm just going to put a diagram here which perhaps is clearer, but maybe not. So imagine at the birth of the solar system, we have the protosun and we have a disk. Material is falling from the molecular cloud, and this disk has a CI-like composition. Then we have a thermal processing event which removes the supernova material, which is in this part of the disk, and puts it in a gas phase. And after that, we replenish the inner disk with inward drifting CI-like material, and the planets here are sort of a mixture between these two types of material, between inner disk material and outer disk material. So this is the model that we'll be working with. And actually there's a recent paper which did some simulation and actually proposed that, okay, perhaps the mechanism that results in the thermal processing are actually outbursts. And in this particular scenario, we have the inner disk, and we have outbursts which are generated by instability when the accretion of the material is rapidly increasing, and the temperature are being elevated. The ice line moves outwards, and we're processing material. So again, if the carrier of supernova nuclides are residing in the ices, then of course these outbursts can easily explain all the data that we have, in the sense that the reason why the inner disk is depleted is because the ice line has moved outwards, and we've got rid of all these ices in the inner solar disk. Okay, just quickly with another model. It's a modification or a variation of what I've just been proposing, and this is published by Matthias Eck and co-authors in 2020. But these people are saying that, okay, there is stardust in the molecular cloud. Some of the stardust comes from AGB star. Other type of stardust come from supernova. And then we have the ISM grown dust mantles here, which are homogeneous material. And as the accretion proceeds, we are thermally processing these dust mantle, and then we're enriching the inner disk in stardust. So this is a variation of the other model, but it's essentially, again, generating this isotopic variability by thermal processes. So they are, okay, so if we accept this model, there are some important unresolved issues. And I would say that the first one, we have no carrier of isotope anomalies with the required thermal properties consistent with thermal processing in the inner disk. So we have no material which is actually not ultra refractory that is carrier of isotope anomalies. So we don't know where those supernova nuclides reside. And the other interesting thing is that when we look at the inventory of presolar grains, there's very little supernova derived grains. They only make 1% of the presolar grain population. The bulk of the presolar dust that we find in chondrite is from AGB star. So we don't have evidence for that. And the other question that would be interesting to answer is whether this water, ice, is it inherited directly from the molecular cloud, or is it processed in the protoplanetary disk? So I want to explore the idea that that basically there's a reservoir of supernova dust in interstellar ices. And I will just start by speaking about a concept that's well accepted in astrophysics, is that when we have a supernova, a core collapse supernova, the majority of dust that is produced by the supernova is subsequently destroyed by both the reverse shock and the forward shock. So we have a supernova explosion, we have the expanding ejecta, and as the ejecta travel outwards and interacts with the ISM, what happens now is that there will be two shocks, two blast waves, a forward shock and a reverse shock. And the reverse shock is hypothesized to basically destroy pre-existing dusty clumps or pre-existing dust. And so in this case, what's going to happen is that the dust is going to be destroyed, and the supernova metal are going to be atomized and transferred into a warm ISM phase. And eventually, this material, when we move the hot ISM towards, when it expands and cools, it's got to either recondense or be reabsorbed by pre-existing grains and possibly ices. So the scenario that I'm thinking about, and this is not new, there's a number of papers here which have spoken towards this, but we produce dust by condensation in the expanding core collapse supernova shell, and then the reverse shock destroys a large fraction of this dust, and the metals from the supernova are ejected into the diffuse ISM, predominantly in atomized form. And in the molecular cloud, the density is high enough for efficient accretion, and so the atomic supernova metals are incorporated into the surface of grains and embedded in the ice matrix. And so this is the scenario that I'm thinking, and this is what I want to test whether or not this is correct by looking at chondrites, which have accreted a lot of ices. But first, let's look at whether or not there's evidence for this in the literature. So I'm showing you two recent papers here, which look at the composition of the material, which is in the tail of cometary objects, but very far away from the sun, where temperatures are well below the silicate sublimation temperature. And that means that, and they've discovered atomic iron and nickel. So one has both discovery, and the other paper here has discovered atomic nickel. And because these temperatures far away from the sun are so low, these are not dust grains that are being sublimated. So the nickel and the iron has to be coming from a volatile carrier. It has to be coming from the ices. So at face value, these results support the idea that the ices are a reservoir of metal. So now we need to look at carbonaceous chondrite. And so again, what I hypothesize here is that we have silicate grains, and these grains are mantled by ices, and these ices contain atoms of supernova nuclides. And how can we test this hypothesis? Well, as I mentioned earlier, carbonaceous chondrite, and actually all chondrites, they contain evidence for the interaction of water with pre-existing minerals. And this is what we call phyllosilicates. So phyllosilicates are minerals which are formed when water reacts with pre-existing minerals. And so if we can find a way of extracting or analyzing just the composition of the phyllosilicate, it should be a mixture of the supernova signature with that of the rock. So minerals formed by aqueous alteration should be enriched in supernova nuclides if our hypothesis is correct. So today I would like to focus on zirconium, and one of the reasons is that zirconium is a refractory element and is relatively immobile. And zirconium has 5 isotopes, so 90, 91, 92, 94, and 96. And you can see that this is in red, this is the S process path. So this is the slow addition of neutron. And in order to make 96 zirconium, you basically need a high neutron flux, because if it's too slow, then you decay back to molybdenum 95. So 96 zirconium is mainly an R process element, so it's made by rapid neutron captures, and it's an element that, or a nuclide that is made in a supernova explosion. So we're going to be using 96 zirconium as a hallmark of a supernova signature in these clays that we find in chondrite. And there's both astrophysical models and as well as data on pre-solar grains. So I'm showing you here the mass spectrum of zirconium, and these are different types of models. But what is the most important thing to remember here is that both these are two supernova grains here that have been identified in the pre-solar grain database. And these are models for a 15 solar mass supernova 2025, and here a slightly different model. But the bottom line is that whenever these models suggest, as well as these grains, that there is large excesses in 96 zirconium in supernova environments. So again, we're taking this idea that an excess 96 zirconium implies a supernova signature. Okay, so now we go back to the chondrites and say, how are we going to do this? How are we going to try to find out whether these clay minerals have a supernova signature in them? And one thing we can do is we can do leaching experiments. So leaching experiments is when we use acid of different strength to try to remove specific minerals. And just to explain you how we do it, we basically take a chondrite. It could be 1.5 grams, 2 grams of material. We crush it, and then we use different types of acid. So we soak the powder in different types of acid, and after that we remove the supernatant and we keep that for analysis. And here, what we've done is these 3 steps here. So leach 1, which is we've put the chondrite 20 minutes in water and then remove the water and kept that. After that, 20 minutes in very weak acetic acid. So this is just like table vinegar, room temperature. And then the last leach here was 1 day at room temperature with strong acetic acid, so strong vinegar. And the rest of what's left after that, we just fully dissolve it. So we're going to be looking at 2 leaches, so leach 3 and the residue. And we don't look at these 2 here. Well, we keep them and we have the data for what they contain, but basically this is just to get rid of the terrestrial contamination. So this is just a cleaning step. And so acetic acid is not very strong. So we think that we can dissolve carbonates, sulfides, sulfates, and partially dissolve clay minerals. And so this is what's going to be interesting. So if we partially dissolve clay minerals with acetic acid, then we should get a supernova signal. We should get something that's enriched in 96 zirconium if our hypothesis is correct. So what material did we look at? We've done 2 types of experiments. We've done leachate experiments. So this is the L3 and the residue that I just talked about. So we looked at these meteorites, Tagish Lake, Maribo, Murchison, a CR chondrite, CV, CO, ordinary, and R. So these are all the major groups of chondrites that we know in our collection. And then on top of that, we've done full digestions of different types of material and their components. So we've looked at normal CIs, normal refractory inclusions, the one which don't contain aluminum-26, though these are the so-called fun inclusion, samples from Vesta, samples from the angrite parent body Mars, as well as a few carbonaceous chondrites here. And the way the data is presented, so we have 5 isotopes, as I mentioned earlier. For technical reason, when we do analysis by mass spectrometry, there is some mass bias, and we must correct for that. And we normalize all our ratios to a fixed ratio, and in this case, we use the 94-90. And so we look at 3 different ratios, the 91, 92, and the 96, reference to 90. And we present the data in the mu notation, and that is just the ppm deviation of the sample relative to a terrestrial standard. So now let's look at the results. What we're looking at here is 2 diagrams. So in one axis is 96, the other one is the 91. And here in axis 96, and the other one is the 92. So these are the 3 isotopes that we said we could measure. And the leachates are in blue and the residue in red here. And you see the axis here is in ppm again. And the first observation is that there is a huge variability. And the variability seems to be controlled by essentially 2 end-member components. So a residue here and anomalous leachate here. Everything in the solar system, at least everything in these leaches, lie on a single correlation line. And the same thing if we plot the 92 against 96. So this at face value will mean that there's only 2 components which generates this variability. However, first we must consider whether or not this is an artifact of not dissolving some presolar grains. I mentioned earlier that silicon carbide is an abundant presolar grain. And here are the mass spectra of the composition of silicon carbide. And you can see that they characterized by huge deficit of 96 zirconium. So to go back to this diagram here, is it possible that because in these leachates we're not attacking most of the minerals, just the clay? Is it possible that these excesses just reflect the fact that we haven't dissolved something that's super negative here? And so we can do mass balance calculation and see whether or not this is possible. And this is what I've done here. So we know the isotopic composition of the silicon carbide. We know the concentration of zirconium in them. And we know their abundance in different types of chondrites. So we can calculate the effect of not dissolving silicon carbide. And this is basically the type of variation we would generate. And that is basically 10 times less than what we see. So clearly, not dissolving silicon carbide cannot be the reason why we have these variability, these large excesses up to 5,000 ppm here for the 96 zirconium. So if the 96 zirconium is coming from these clay minerals that are in the matrix, we should possibly see a correlation between the matrix abundance in chondrites and the amount of zirconium that we recover. So this, we've tested for this, and this is the plot here. So the amount of zirconium is basically, if I look at a particular leach, how much of the zirconium is present in this L3 fraction as opposed to the total budget of zirconium of that particular chondrite. And you can see that the amount of zirconium recovered is much greater when we have a lot of matrices. So for example, in these sort of CM chondrite, which have up to 70% matrix, that's where we have the most zirconium. And that makes sense. That suggests that this anomalous zirconium is actually coming from a phase which is hosted in the matrix. And so 99% of the matrix is actually made of these minerals that we call clays. So these are the so-called phyllosilicate, and I don't want to get into the details here, but the bottom line is that these phyllosilicate or clays, they're layers of mineral layers which are interlaid by different types of molecule, including aluminum, magnesium, and iron. So if we are actually, there's a huge literature on the leaching of clays, because people use that in the industry to remove pollution from grounds. And so they basically activate the clays by getting rid of some of these ions here, and then use these activated clays to basically suck up polluted or metal pollution. So, and this literature tells us that if we actually are slightly leaching the clays, we'll get rid of aluminum, magnesium, and iron. So then I want to do the same experiment as I did earlier. So I want to look whether or not aluminum, magnesium, iron that is present in the leach correlates with the amount of zirconium that we've recovered. And so these are the results again. So the fraction of zirconium recovered in the leaches versus aluminum, magnesium, and iron also correlates. And so that basically, to me, supports strongly the hypothesis that the anomalous 96 zirconium is basically carried by the clays. And if I look at, for example, a carbonate phase, if I look at the calcium, we can see there's no correlation. And so the anomalous zirconium is not in carbonate. It looks like it's associated with the clay minerals. So that suggests that the excess 96 are mainly hosted by phyllosilicate, and it supports the hypothesis that ices are the carrier of 96 zirconium. So one question that we need to ask is there any evidence that clays actually contain zirconium? Because this is not something that people have looked at in the literature in the past. I mentioned Ryugu earlier. It turns out that in this extremely detailed paper by Nakamura in the supplementary information, I found this table here which reports the analysis of the phyllosilicate matrix, and these values here are in ppm. And you can see that there's approximately 10 ppm zirconium in phyllosilicate in Ryugu. So that means that the phyllosilicate are a reservoir of zirconium, and this again goes into the same direction as I've been discussing. There is anomalous zirconium in the phyllosilicates. Okay, so now the next thing that we need to explain is why is there variability here? And if we look at the different types of meteorites, so the meteorites which basically have the strongest anomaly in both 91 and 96 are the most pristine meteorites. As with a decreasing excess here of 96 and 91, we look at CR, CV, ordinary chondrite, and R chondrite, and basically these meteorites have all experienced variable degree of thermal metamorphism. So what I think is happening here is during thermal metamorphism, what happens is that the zirconium, which was leachable before from the matrix, now is transformed or enters a mineral which is no longer leachable. And the R chondrite are basically the chondrites which have the highest metamorphic grade, and there are the objects here where the residue and the leach is basically almost identical. So that is consistent with this idea that during thermal metamorphism, we are actually locking some of this anomalous material into a phase which is not leachable with acetic acid. So then I would say that this would be the minimum composition of the pure ice member here, recorded by CM as well as Tagish Lake. And the ice-free end member would be recorded by the most negative composition here that we see. So this would be the ice composition. This would be the rock composition in this model. So we can actually compare the pure ice member, the isotopic pattern of the pure ice member with supernova models and supernova grains. And this is what I'm doing here. And so in blue here, I have the leachate. So we're looking at 90, 91, 92, and 94, and 96. And the 94 and the 90 are the normalizing isotopes, so that's why they're fixed. And what I've done here is I've taken the composition of supernova shell models, X-type grains, and pre-solar graphite. These are all supernova signatures, and I've normalized them to the anomalies that I find in the leachate. So everything is normalized to 5,000 ppm 96. And these are the patterns that I see. And there's a surprisingly very good match. The leaches, which are in blue, provide a very good match with the pre-solar graphites, as well as the X-type grains and the supernova shell. So this again supports the hypothesis that the signature that we find in the leaches, which is the anomalous zirconium present in the clays, is derived from supernova. And here it's a highly diluted component, and it's approximately 0.05% of the true supernova signature, depending on the model assumptions. Okay, so So now we think that the ices are a carrier of 96 zirconium. So let's see what the solar system material, see where it plots relative to the mixing line that we've derived from the leaches. And so these are the data here, and I'm just going to show you what we have. So the blue line here is 96, 91. So the blue line is the regression that I've obtained from the leach. So that's the line there, and then I've reported the composition of fun CIs, the non-carbonaceous material, including Mars, carbonaceous material, and canonical CIs. And for reference, I've put the residue here. And that's very interesting because some of the most anomalous objects that we have in the solar system are fun CIs and canonical CIs, and they plot exactly on that regression line from the leaches. So it means that basically all the variation that we see in the solar system is two-component mixing. So a rock end member and an ice member, which is highly anomalous. And where does the Earth plot in this diagram? Well, the Earth plots here. So you can see that I've talked about earlier that Earth for zirconium was an N-member composition requiring a missing reservoir. But you can see that Earth is not an N-member composition. We have fun CIs and the residues here, which are more anomalous. So Earth plots in the middle of that correlation. And so the idea that Earth is formed from a missing component and there's a missing reservoir can be abandoned. And so I will do like this. Like we can forget about this idea that the Earth is an N-member composition for zirconium. In contrast, it supports the idea, and going back here, that these objects formed by mixture of ice. So that would be the material which is from the outer solar system and the inner solar system material. And so it supports the idea that I've been promoting that the Earth is basically a mixture of non-carbonaceous material and carbonaceous material. Okay, so let's look at the implications now if ices are a carrier of isotope anomalies. And the first thing that I want to explore is whether or not the 96 anomalies are tracking water. So if we look at a 96 composition of a body, does it reflect the amount of water ice that it has accreted? And so what I'm showing you here is the composition for the angrite parent body, so the 96 composition here versus FeO. And of course, FeO is taken as a proxy for the oxidation state of a planetary mantle. So the more FeO that you have in the mantle of a planet, the more oxidized is a planet. And so we can see here that there's a very interesting correlation with the anomalies in the FeO content of planetary mantle, with the Earth being the most the most reduced of these objects. And so I would interpret this correlation as reflecting a decrease in the accreted ice content of the angrite parent body, Vesta, Mars, and the Earth, as evidenced by their FeO content. And so the prediction now, if we would analyze Mercury, which basically has almost no metal or no iron in its mantle, Mercury would be negative relative to the Earth if this model is correct. So that's a prediction. We could possibly test this by looking at reduced chondrites. For example, now I forget the name, but it doesn't matter, a type of meteorite which is formed under highly reducing condition, which could be taken as a proxy for the formation of Mercury. Okay, so Earth lies a little bit away from this trend, and a possibility is this is the effect of pebble accretion. And why is that? Yeah, I forgot to mention that you can do the same relationship with the core fraction. So the more reduced a parent body is, the more you're putting iron in the core, the larger is the core. And the relative core fraction for Vesta, Mars, and Earth also correlates with the 96 zirconium. But going back to pebble accretion, what happens in pebble accretion is that during the evolution of the planet, because of the accretion luminosity associated with the pebble flux, the planet develops a hot envelope. And this is a very well understood astrophysical phenomena. This is a paper which discusses it. But you can imagine that what happens with the icy pebbles as they're traveling to envelope, they are thermally processed. So there is a ice line in a planetary envelope, so that means that you get rid of the ices. At one point, you will not be accreting ices during the evolution of a planet by pebble accretion because of this hot planetary envelope. So that's a way you can explain that you can only accrete ices in the early stage of the evolution of the planet, because as soon as you form this envelope, then you shut down the accretion of volatiles. So this is a reason why you could have basically this shift here. This could be a signature of pebble accretion. Okay, so the other thing we can discuss a little bit more is the ice-rock ratio. And I'm showing you here again the 96-91. This is the ice-free end member from the residue. This is the ice end member from the leachate. And these are mixing lines here, which represents 5% in mixing of ice. This is Bizzarro, this is 100%. And the observation is that the solar system lies here. All the objects in the solar system, they have very little variability. And if I expand this here, it basically suggests that all these different bodies that we have, so going from the Earth all the way to the carbonaceous chondrite, the variation is only approximately less than 5% of ice accreted by mass. So this would suggest that the first generation planetesimal all have the same rock to ice ratio, if this is correct. There's some assumption here in this calculation. These numbers will change depending on the model assumptions, but the range will not change. So the first order observation here is that there has to be, if those end members are correct, there's very little variation in the ice to rock ratio of planetesimal. And that would suggest that, so there is this idea that the snow line is an important region to forming planetesimal. So there's several papers which I've promoted this idea, and our data which suggests a very limited variation in the rock to ice ratio would support that the majority of first generation planetesimal must have accreted either at the ice line or beyond the ice line to have a similar ice to rock ratio. So there are these models which promote the idea that there is a pressure bump at the ice line, and you form planetesimal in this environment. And so if that's correct, then the majority of planetesimal formed in this environment would have the same rock to ice ratio. It'd be interesting to look at highly reduced planetesimals, because the prediction would be that they would not have this ice component, and relative to Earth, they would have a different isotopic composition. So that's all I had to say. So in summary, we believe that interstellar ices are a carrier of anomalous core collapse supernova zirconium. The isotopic variability in the solar system that we see for zirconium basically reflect two end members, rock and ice. Earth is not a compositional end member, so there's no missing reservoir. And the 96 anomalies can track the water ice accreted by different bodies. First generation planetesimal have a similar ice to rock ratio. It may reflect accretion at the ice line. And the last bit, which I didn't talk in detail, but because we have also chondrules in those different chondrites, it must mean that they don't have a residue composition. So they must be that some of these high temperature solids must have equilibrated with interstellar ices. So thank you very much. No. So we haven't done titanium, but we have a database where we measure basically the periodical table in each of these leach and residue. So we know what's in there, and we know what we can potentially do. But we haven't done titanium. No. So zirconium is the only thing we've done now. Well, so it's a bit complicated because some elements are more mobile than others. So, for example, I didn't mention this, but So zirconium and molybdenum have a very similar nucleosynthesis. And so you could think that, I just showed this diagram here at the very beginning, you could think that you can potentially do this as well. For molybdenum 100, it's also our process element. The problem is that molybdenum is extremely mobile. And so I think that the same thing for zinc or these elements, basically the signature is everything's equilibrated in a chondrite. And so you will not be able to basically parse out this specific signature. You can with zirconium, but I predict that molybdenum will not be the case. And so not many elements are suitable for this work. Yes?
You said there is no variability between the NC and CC chondrites. Does this mean that there is no spatial or temporal variation in the zirconium content in the interstellar ices?
Okay, can you repeat that again, please?
No variation between NC and CC, does it mean that all the interstellar ices are the same?
So let's just go back to one plot here. So there is some variation, right? If I go back, yeah, that plot here. So you can see that the reason why I said there's no dichotomy is because if we analyze CI chondrite plot at the same region as Mars. So it's not on this plot here because when I made this original version, I didn't have the composition of CI chondrite. So there is CC material which plots in the carbonaceous, the non-NC field. It just means that they've accreted similar amount of ices. That's what it means.
All the ices are the same?
Yes. In this model, all the ices have the same composition. Yes, of course.
And I'm also curious, how do the atoms get locked in the ices? How do they escape condensation into solids?
How do they escape condensation? I think there's just not enough, the density is not high enough to condense in solids. So I think you condense in atomic form because the density are not high enough.
Are there some modeling on this?
So I think you can look at these papers here. If you look at these papers actually discuss. So take a picture if you want.
I wonder what would be the effect of a giant impact, at least in the case of the Earth, assuming that probably the proto-Earth and Theia would have slightly different composition. Can you see this, for instance, in your measurement? Could you explain another time that the Earth is a bit outside the train? Let's say that there's different scenario for the giant impact. So you have the canonical scenario is a 10% impactor and 90% for the proto-Earth and 10%, and the other is 50-50. So of course So the effect of a giant impact, the composition of the precursor material will be preserved. So it depends what it's difficult to predict, because I would if both bodies have the same composition to start with, if they're the same size, our model would predict they have the same composition. If one of them is very small, then its accretion history, depending it forms by pebble accretion or not, will be very different. It will have incorporated probably much more ices. So that could potentially have an effect. There's no ultra high precision measurement for the moon yet, and so that could potentially show a slightly difference, but I would predict not. That's my prediction. The other thing that I should mention also that I forgot to mention when I was talking about ice accretion and the FEO of planetary mantles is that, so of course, the angerite parent body is one of the most volatile depleted body that we have in the solar system. And here I'm trying to convince you that it has accreted the most ice. Remember that all these bodies had magma ocean. And so the magma ocean stage can get rid of the volatiles, but the zirconium, which is in the ice, will stay in the planet. And so you'll get rid of the
volatiles, but zirconium is refractory, it will stay in. So it keeps the signature of the ice even though there's no more ice. Yeah.
I'm curious about the consequences of this prediction. So are you saying that even including the terrestrial planets, their cores are forming outside of the ice line?
Yeah, I mean, so I would say that the Earth accreted at the very before the formation of the planetary envelope. That's the time where you can accrete ice. So the Earth, I mean, accreted beyond. Yeah, I don't accrete outside the ice line. Well, that depends. I mean, a lot of models suggest that the ice line was about 1 AU in the first 2 million years. So it depends. I mean. So, but I would say that, yeah, I mean, the Earth accreted beyond the ice line, because else it would not have the signature. So that's what I think.
So even though the ice line is preserved somewhere outside, your model still predicts that maybe some terrestrial planets have migrated to where they are.
Well, so the only planet the only planetesimal which might form within the ice lines are the orbites, for example. These highly reduced planetesimal, they don't have any iron in them, so all the iron is in the core of the planetesimal. Mercury, I would say, would be the same. So I would predict that Mercury's signature and possibly these orbites, these Mercury-like samples, will be more negative than the Earth, if that model is correct. Well, we might not have a piece of Mercury, but we have these different types of meteorites, which are sort of, you can use them as a proxy to study, Mercury-like protoplanetesimals, because they are highly reduced. And so that would be interesting to do these high precision measurements for orbite, for example. And then there's a number of new meteorites now which people have proposed that they could be from a Mercury-like protoplanet, or at least asteroids which form the same region as Mercury. So that would be interesting to do for zirconium.
This may be maybe a stupid question, but is there a way of, because we can't do it for in situ measurements for our sun, but is there a way of looking at, let's say, protostellar ices and seeing if this scenario holds true or not?
I think for zirconium it would be very difficult because the concentration are not very high in the ices. So I mean, sample return mission to an outer solar system object which still has ices, but that's not going to be in my lifetime.
Can I ask a silly question?
Yeah.
So what is the first generation planetesimal? You said.
Yeah, first generation planetesimal. So in my view, there's two time during the evolution of a protoplanetary disk where you form planetesimals is at the early stage where the dust-gas ratio is high, streaming instability works very well, and so you form a lot of planetesimal. And at one point where you start clearing the disk, you increase again the dust-to-gas ratio, and then you can make the chondrite parent bodies after that. These are second generation planetesimal, I would call them. So the first generation planetesimal are the planetesimal which all have incorporated aluminum-26 and are molten. These are all the molten planetesimals, like for example, Vesta. That would be a first generation planetesimal. The bodies which are chondritic in composition, which have never been molten, I would call them second generation planetesimal. But that's something I would say it's not something that's unanimously accepted. So this is just my view. That's how I call them.
And also, how far is it, the snow line from the center stars? Typically, how far is it?
Well, so I guess it varies a lot, right? Because so when you have an outburst, a stellar outburst, I think the snow line can go back to 10 AU or something like that. So I think without outburst, there are different models, and for example, this is just a diagram, but you could basically say this is, let's say this is 1 AU in the early evolution. Then you have an outburst, it moves to 10 AU, and then as the temperature decreases, it moves back to the inner solar system. And so, but this is model dependent.
Would that change your results?
I mean, I don't think it doesn't change it would change the dynamics of how material is thermally processed. So it would be like the details of the model would change with the position of the ice line, but the general observation that the ice are carrier of anomalies would not change. But it would change how material is thermally processed, how you get rid of this nuclides, the 96 zirconium. That would change. That could give rise to some complexities in the data, sure. That's possible.
Would that change your mixing fractions or anything?
I don't think so. I don't think that would change that, no.
Somewhere.
Because remember, you know, the ice line, if we look at differentiated planetesimal, for example, they basically, they're not affected by because all the ice signature is locked into the body in the first million years, because they have to accrete very early in order to differentiate. So the zirconium is locked in the planet. As soon as you transfer the zirconium from the ice to the silicate part of the planet, then it's frozen. It doesn't move after that. So I don't think it will change that the ice fraction mixing that I put forward. But again, we have to take this with a grain of salt because there are some assumptions. You need to know the concentration of zirconium in the ice, and that requires some mass balance calculation. And yeah, it's not bulletproof. Let's put it this way.
When there's an outburst that evaporates all the ice mantles, where does the zirconium go?
It goes into a gas phase, and so this is the reason why I think that, you know, okay, so let's go back here to show you this diagram here, and then I'll show you the data that supports this idea. Sorry, it takes a bit of time. Yeah, so this thermal processing here basically removes the ices, and the zirconium that's in the ice goes into a gas phase. And then if you condense something from the gas phase, you should have a 96 enriched signature. So do you remember what we condensed from this gas phase early on? CAIs. Okay, so what does CI have for composition? And that's where I show you the plot here. Yeah, so this is early material. So these are the canonical CI. So these are of all the planetary objects and components, the canonical CIs, which are sample of this gas phase, have the more anomalous composition.
But the outbursts can also have a much later
Yeah,
several episodes.
yeah, it's true. But at least let's say there's several episodes. But if you don't form CIs, well, the gas is just going to be accreted to the sun, right? So.
But it's canonical. So you're saying it's canonical CI, so that means you have our canonical.
Yeah, so these are all the CI. We call them canonical CIs because they contain the canonical abundance of aluminum-26. That's the reason. And the fun CIs don't contain. They don't contain aluminum-26. And it's very interesting that they define the two end member composition in the planetary material, the fun CIs and the. And again, it doesn't. To me, it's not consistent with the idea that the fun are just like heterogeneous sampling of various pre-solar components. Here, they just basically lie on this correlation line, and two independent fun CIs give the same result.
I missed a detail. Did you take the plot of the chondrites or just the metrics?
For these ones, these are bulk measurements of Mars and bulk chondrites, and these are the residue. They are the residue that I showed at the beginning. Yeah.
Maybe there is one thing I don't follow well. So according to your scenario, the zircon is incorporating in ice.
Yeah.
Very early in the solar system.
So in the molecular cloud, before, yeah, and then the ices are accreted together with silicate in the disk.
So is it possible to have a similar process after or during the formation of planets? Because I guess supernova may also have exploded in some environment all this time.
Well,
And is it possible that some zircon from later supernova have been incorporated in ice?
I mean, this would require that you have a supernova explosion in the vicinity of the solar system
And I think this, what people think is that this would basically wipe out the protoplanetary disk.
It'll be risky.
So this has to be an inherent, this signature has to be molecular cloud signature, I would say.
There is, I think, if I am correct, there is also some theory saying that supernova have exploded even recently, a few million years ago, and we see the traces of this.
Yeah, so this is the Iron 60 story, right?
The iron 60.
Yeah, yeah.
So why not zirconium?
Why not zirconium? Well, it would be very difficult. The contamination is so, the reason why you can see with Iron 60 is a short-lived nuclide. It doesn't exist, there's no Iron 60 on Earth. Then you can basically see it, but zirconium, you wouldn't be able to see it.
But it's still possible that you have some contamination.
But it would never be enough material to change the composition. The mass balance wouldn't work.
Okay, so no more question, right? Let's thank Marty.